all those simple or weak classifiers ready. And the next step is to build our AdaBoost classifier. So let's open up a new cell for the AdaBoost. Here we give it some note, AdaBoost implementation. Have this cell as a markdown. We can put it here. This is AdaBoost. So remember, AdaBoost is an iterative algorithm. In several iterations, in each step, we will employ one weak classifier to process the data and assess the classification performance of that particular weak classifier and reweight the data accordingly. Good practice is to list those steps of an algorithm and in the comments of the program, so we can follow the steps one by one. Okay, first we will do a number of iterations. Okay. And for each step, in each step, select one weak classifier, classify the data, and assess if the classification is correct. And, okay, compute the classifier weight. We call it alpha. Okay. And update the sample weights, call it D. Okay, and we can of course note that the equation for computing alpha, first we need the equation of computing the weighted weighted errors, that is epsilon, the t of the t step, that is the summation over all the samples, the error at is error. Right. Compare the weak classifier HT's prediction with that of the label of the training data. Weighted. The classifier's weight will be alpha. Alpha is the half of logarithm of the correct rate over the error rate. FC over and the change of width of simple width should be exponential of plus or minus the alpha t, that is according to whether the sample has been classified correctly or not using that particular weak classifier. Okay, we have a typo and we need to separate these lines in the math note. Right, here is our note to implement the AdaBoost algorithm. Say the number of iterations, let us give it to a variable. It is a good practice to give some constant of the algorithm to some variable, and in this way we may adjust the behavior of an algorithm by just changing some numbers, and we put all those numbers in one place in the code, so we can experiment with the algorithm conveniently without going over all, if those numbers scattered in over all the codes, and if the code is long, that will be difficult and error prone. So for each of these iteration steps, remember that range gives us an iterable object. We can think that is a list if it is in the for loop from 0 to t minus 1. Okay, and in the following steps, implement the iteration step. Select one weak classifier. In this step, because we have only finite number of weak classifiers, we can afford use each of those classifiers to predict the target value y from each of those x, and select the best one according to the weight, simple weight. Of course, we need to initialize simple weight here. Let the first simple weight to be just nothing.1. Okay. Remember our data matrix X is an n by 2 matrix, and n is the number of samples, and the weight needs to be equal to the number of samples. To have the number of samples, we put x shape 0 here, and the shape of an array, just how many entries in each dimension. Let's check x shape. That is 400 by 2, because we have 200 samples of each class. This 400 means 2 class by 200 per class. And of course, this shape itself is a list, is a tuple of 2 elements. Here we take the first one of the tuple, that is 400. Okay. And that is to be divided by this n of, sorry, not minus, x.shape 0. This way is much better than if we just put a constant 400 here, because in future, if we want to change the number of samples we would like to play with, we do not need to change this piece of code. It changes automatically with the size of the data. Then we let each of the classifier to predict on the data. Remember the prediction of the data using the classifier. We just see simple cut x with the classifier parameter, and we have the list of parameters in H. Okay, have a review of what H is. H, let's see the first 5 parameters. Okay, they are here, and we have several examples of H here. So in this step, we need to take each parameter set from the list of H and put this parameter set into the input arguments of the weak classifier, and make take note or record the output of the classifiers. Remember the list construction syntax of Python. Okay, we can have this prediction as an element, as the elements in a list, and remember the syntax of expanding the tuple or list element in the argument of a function. This star symbol and H. If H has 3 elements, it will put H0, H1, H2 here. Okay. Of course, we need to have H specified here. So for H, and we take each of these lower H. Let's write it as H underscore. We need to take each of those H underscore from the capital H, the list of all possible weak classifiers parameters. Okay, in this way, we have constructed all those. We have let all the classifiers in capital H to predict on the data. Okay. In the next step, we want to, because that is the selection to do here. So in the next step, we want to assess how those predictions compared to the supervision target value. So what we want to do, see if the prediction simple prediction as a number of 0, 1 values, and we compare it to the y value. So we need to compute the errors. So we take the value of if it is not equal to y. Okay, remember the way to convert this true false values to 0, 1. We take an S type of float value. Of course, we need to compare each of the predictions in the in all the predictions to do this comparison. And in the last step, let us save the result of the last step in a variable. Set basic cutter prediction. Let it be here. And now the next step is to take every prediction in this basic cutter prediction and compare it to y. That is a full simple prediction in those basic cutter predictions. So in this way, we convert the predictions into errors. Okay, let us say that to be basic cutter error. we can use multiple lines for one instruction. That is to now we have the error of each of the weak classifiers ready. Okay, we want to compute the weighted summation of the error on all the training samples. So that is to do, let the 0, 1 representation of the error multiplied by those sample weights. This is a weighted error, and let us take the summation of this error over all the samples. For those error, we need to take this element from the list of basic cut errors. For error in basic cutter error. Let's name this to be basic cutter cost. Now we may want to make sure that those computations are making sense. So let us have a sanity check before we proceed. First, let's change the iteration times to be only 1. So we just do the computation once in the first step and have a look how those variables to be. And let us print the first 10 elements of those basic cutter cost. Okay. Basic cutter cost, the first 10. I would suppose that because the first 10 element, if you remember from the last part of this tutorial, that for the first few cutters, we classify because the cutting boundary is outside the entire data set. So those classifiers either predict all the data samples to be 0 or predict them to be 1. In this case, the error number should be around half of the samples, that is about 200. Let us see if this is the case. Okay. Yes, actually, because we are computing the weighted sum of the errors, so all those error rates for the first few classifiers to be very close to half. In fact, they are half. Those are numerical fluctuations in the computer, but that doesn't matter. Okay, so the output is as expected, right? Okay. In the next step, we need to do our selection of which weak predictor we would like to use. To do this, we will employ the minimum finding function provided to us by NAPI. That is called as it in the math called argmin. If we take argmin from a list, and that list is to be basic cutter cost, it will return the index of the smallest value of a list. Let's have a look at how this behavior. Okay, see we have a list here. This list can be an NAPI array or any array-like object. Let it to be 1, 2, 3, minus 1, 1, 2, 4, 4, 4. Okay. So the smallest value in this list is of course this -1, and the index for that is 0, 1, 2, 3. Okay. The index of this A underscore is the 3, the fourth element and the 3. Let's see, print nappy dot argmin A underscore 3, right? We can further investigate this, like let it to be some random number. Remember our random generator? Rand 100 number. Okay, let's print the element of this, and 100 is to be too much, maybe 20. And the element itself, that is the 14th. Actually it is 15th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. So this is to be the smallest number in this array. To be completely sure, we can print the minimum value of A. Oh, actually, we can just print A. Yes. Okay. Look, the same number. So this is how we find the minimum value from a list. That is the minimum value of the list. Let's say that is the best basic Carter index. That's Carter index to be this one. Now we have the weak classifier chosen. In the next step, we need to use this classifier to classify the data. Actually, it has already been done, saved in this prediction and the error saved in here. We just need to extract those predictions and errors from those lists. Okay, let the Carter itself chosen to be this best Carter index of the collection of all Carters. Okay, and so let the error score to be this basic Carter cost of the best Carter index. Okay. Remember our discussion of the minimum, the behavior of finding the minimum value and taking its index. This is expected to be just have it this way. Basic Carter cost dot min. But we can rewrite it in this way to be explicit. Okay. The extra errors is to be basic Carter error, best Carter index. Okay. And now let us compute our alpha here. Okay, alpha equals half of NumPy log. In NumPy, log means log with the natural exponent, the base of a natural exponential, and here that is the 1 minus error score over error score. Okay. Now we have the weak classifiers ready, and we have its weight ready. Next, let's have an ensemble container to collect those weak classifiers. Let's say cutter ensemble to be an empty list, and have this to be collected. Cutter sample dot. Remember the other way to construct list to use append. Now we have this cutter chosen, and its weight here. The last step is to update the width of the samples for next step of iteration. To this, that has the change of width to be computed using this equation. This minus or plus the weight of this classifier. Let's have this NumPy exponential. Okay. To have the -1 or +1, there is a minor implementation difference between the algorithm we discussed on paper and the implementation here. On paper, we use +1 and -1 label for the predictions and the labels given by the training data. But in this implementation, to be easier for dealing with those binary comparison results, I choose to use 0 and 1. To convert 0 and 1 into -1 and +1, we need to do 2 times error minus 1. Okay, look at how this equation makes sense. If the error is 0, 2 times error is 0, and the final result is to be -1. If the error is 1 and 2 times error is 2, and this subtract 1 from 2, we arrive 1. So when there isn't error, the result is -1. When there is error, we have +1. Okay. This minus or plus switch is multiplied by, of course, alpha. Okay. And let this change applied to the width of the sample. In the next step, we need to perform the normalization. Let each element of D to be divided by the sum of D. Okay. For example, if this step is to ensure that the summation of the final result of D equals to 1. Let's look if A underscore equals as a read, say it to be 5 and 15. Okay, print A and A dot sum. Now we have, of course, the summation is 20, and let each element is divided by the summation of this 20, and then let's print again, right? This is the effect of normalization, and that is a commonly practiced operation. Now we have completed our construction of the AdaBoost algorithm. Of course, in the iterations, we would like to check if the algorithm performs well, perhaps a very easy way to do that is just print the performance of the current prediction of the ensemble. Okay, let's call it round. Remember the formatting of a string. Okay, a good practice is to write the placeholder and the variable to be printed altogether. Round t and error number is another. Okay, that is error number. Let's call it ensemble error num. To compute the error num of the ensemble, we need to use this ensemble to do predictions. The prediction of the ensemble, we need to use each classifiers in the ensemble to do the prediction. So let's use simple cut x, and at this h underscore for each of the underscore in the ensemble. Oh, not this one. That is quarter ensemble. But this is not enough. Remember, we need to weight the prediction of each of the weak classifiers by its importance. Let us call that A underscore. And it happens that in each step, we pack the weak classifier parameters and its weight together in the ensemble list. Okay, but this is not the end. We also need to do the conversion from 0, 1 to minus and plus 1, so that the weighted sum makes sense for as derived in the AdaBoost algorithm. So let's use this conversion. Okay, now if the prediction is 0, that will end up with -1. If the prediction is to be 1, it will be 1 again, because 2 times 1 subtracted by 1 is 1. Let the prediction to be this. Ensemble prediction. And make a list of that. Right, as ensemble predictions. Note that the predictions is a list of predictions, and in each element of the list is the predictions of from one weak classifier for all the samples. So if we make an NP array from these predictions, we will end up with a matrix, and each row of the matrix corresponding to one weak classifier is a prediction on all the trained samples. So we need to take the sum, actually the weighted sum, over all those predictions, using this sum along a particular axis. Okay, let's have a look at how this operation does. See if this is a NP array. Okay, and let us two rows, 1, 2, 3. Right. If we take the sum of this array, it will give us the summation of all the elements. Okay, but if we have a partial sum of this array, what we need is to take it along some axis. Okay, look, this is an array or a matrix, and if we take the summation over the rows, the resulting array will have the same element as the number of columns of the original array. So that is 5 plus 1 equals 6, 15 plus 2 equals 17, and so on for all those columns. If we change the axis to be 1, it will do the summation this way. Okay, hold on. The result is written in this one-dimensional array without without putting it in the vertical way, but the first element corresponding to the summation of the first row and the second element corresponding to the summation of the second row. Okay, here we need to summation along the rows. That means to sum all the predictions of all those weight classifiers weighted by their corresponding weights. Okay, this is our prediction, and the error, of course, ensemble errors. That is if ensemble prediction, if this is greater than 0, this is actually dichotomized this prediction into two classes, either to be the first class or the second class. If this isn't the same as the supervision, the labels given by in the super training data, that would be counted as an error. We do not need to actually do this. We can directly using navi.count non-zero the errors. And now it's ready to run. Let's have a look how this algorithm behaves. Well, here we have an error. Well, I think that is because the comparison of the ensemble prediction greater than 0 is actually binary list, and that is not an NP array. So for a non-NP array object cannot be directly compared to NP array object. So we need to convert the type of the left-hand side of the comparison. Yes, this works. And look, the iterations and the number of errors. Okay, at first we have a lot of errors, and the errors gradually reduced. If we do this enough for sufficient number of iterations, of course in this case, even if we do infinite number of iterations, we may not be able to reach 0 errors, but if the hypothesis set that capital H, this capital H here, if this is rich enough, we may be able to reach 0 error in this part. Okay. Now we finish the construction of the AdaBoost algorithm. So far we have constructed the AdaBoost classifier, but it is a good practice to visualize the behavior of our algorithm. And this is a simple enough algorithm, although, but in some complicated procedures, visualization of the data and how the algorithm behaves often helps us to understand where the problem is and to improve the solution. To visualize it, of course, we need to first set up our canvas. Remember the command to set up the comments is first to allocate a window, and then to have some axis as a canvas on the window. In this visualization, I would employ 3 subplots as our canvas. If we give 2 parameters to this subplots, remember there is one subplot command and another is subplots. The subplots actually allocate window and the canvas for us. Let's do some setup. Set size in inches. I would like to have 12 by 4. The first parameter is the width of the window, and the second one is the height of the window in the unit of inches. So here is our window. For the 3 subplots, I would like to, in the first one, we draw the samples with their width indicated by the size of these points. Look at these points; they are all the same, but in the visualization of the behavior of the algorithm, a good piece of information is how the algorithm weights those samples in the beginning of each step, because the cost is computed against those widths, right? Okay, let's set up the first canvas to have easy typing. X is 0. We first give the first canvas to a variable. So let that variable, I'll copy the drawing code from above, that is the scatter, right? And we will do some adjustment. We call the scatter and draw the x and y coordinates that are the 2-dimensional points on the canvas. And also we use in this drawing, I would like to use the actual the ground truth symbol as the color, so we know which point should be classified into which class. We use the same color map, which allows us to compare it to previous drawings, and those minimum and maximum possible value are the same. We need to change the size here, so it according to the actual weight of the samples. Let this 64 to be the base size, because that looks pretty good here. And with this base, if the weight of the sample just to be the same, the original one, such as this one. This is initialized weight. Each point is weighted as the inverse of the number of all the points. So to bring this value to 1, we need a factor of the number of points. Okay, right? If we write it this way, initially all the points will be drawn with the size 64. Okay, but here we need to do some adjustment. Remember, we would like to investigate how the algorithm views the samples before this step of iteration. But now the weight has been adjusted by those previous processing steps. So let us have some buffer for the previous weight. Weight old equals weight. Okay, that is the old weight has been saved here. We use this good to draw. Okay, and let us set up the canvas, other properties of the canvas here. The limits, ticks. Okay, for the title, we would like just to see this is round. Which round it is? It is the teeth round. Okay, round teeth. We need a comma here to show that this is extra. Is actually a tuple. So, so much for the first subplot. For the second one, let us have a XS. Have our canvas ready here. We also draw the data points, but for this one, I would like to investigate how the particular weak classifier chosen by this step behave on these samples. Okay. To draw the behavior of this weak classifier, we need to draw all those samples, and in this drawing, let's use the uniform weight, uniform size of the samples, and we need to change this part. That is the color of the samples. That should be according to the classification given by this the chosen cutter. Okay, and actually we can use its prediction computed here for the color. Okay, let's write it here. Basic cutter prediction, and which one it is? It is this one. This line is a bit too long. Cut it here. Okay, if we use the color to be determined by the prediction given the chosen cutter, we will see how the chosen cutter behaves on this classifier. Okay. We would like to set up the properties. Okay, we need to remove properties of this particular subplot. Here we need to remove this X. Right. Okay, and remember this format. We will output the information about the basic cutter chosen here. Okay, and in the third panel and the third canvas, I would like to investigate how the ensemble classifies the samples here in this step. To do this, let us draw the samples. Using the prediction of ensemble as the color. Okay, but remember here in the ensemble predictions, we have converted the range of the prediction from 0 to 1 into -1 to +1. So to have the consistent scaling of the colors of the prediction, we need to change this minimum possible value from 0 to -1 here. Okay, and I also wanted to, because that will be the prediction of the ensemble of the each of the samples. And that is a real valued prediction. It is a number. It's not it's a fluke number between 0 and +1. If we want to have a decision on each of the samples, that is to be this. I want to show the result of this dichotomized prediction. Okay, and let us just write it here. Ensemble prediction, say dichotomized equals. If this is greater than 0, as type numpy dot float. That would be a value between 0 and 1. Let's scatter this value. Draw the point according to this value. Okay, and the minimum possible value for this one is 0. We do not want this second joining to overlap completely with the first joining, which will cover the first one, original one. So let's use a smaller size. Say it to be 16, which is much smaller. So in the middle of each of the points, we will see how the final decision for each of the points. Because in the joining function, some of the joining functions of the matplotlib library will clear the canvas before it starts drawing. To be sure, we want to have this switch set. So hold to be true. That means whatever joining function, notice do not clear my canvas. I want you to draw on whatever it has already been there. Then let us do some setup of the canvas. And now we are almost done. But we need to notice that because the running of the program is very fast, so generally we will not have enough time to inspect carefully of the behavior of the algorithm. So a good idea is to save the joining to pictures, and we can inspect them later. To do this, remember the figure object, that is the window of on which all the three subplots lies, and use this figure. We can have this save figure function, and let us save it to the temporary folder we have created. That is this temp data. Let's type it here. Temp data. Okay. Say that to be step. Okay. .png. This function will automatically recognize this extension and save the picture in the according form. PNG is to be some bitmap picture. Notice this is a placeholder here. We want to save to a different picture for each of the steps. So we can provide the step index to the file name. But we wouldn't, because there are many steps. A good idea is to, instead of using step 1, step 2, step 3, we better use step 001, 002, 003. In this way, the file name is neat. The trick to do is to format the string, use 0, 03, that means 003D. Okay, and let's run the program. All right, this time we have the files neatly sorted for us. Have a look of the algorithm. Okay, in the first step, all the samples are equal, and the separation, the weak classifier we choose is to separate the plane in this way. And of course, now we have only one classifier. The ensemble behaves the same as the first classifier. Let's see what happens in the next step. Of course, if we classify the sample in that way in the previous step, we will have many misclassification in this part of the data. Okay, and now reasonably the algorithm choose a classifier to try to put this part of the data into right place. And if we carefully inspect the color here, we can see that although the final decomposition is the same as the previous step, but the prediction of the samples actually changes. Look, this part is not as green as previously. Okay, and so what happened in the next step? Oh well, the classifier happens to decide to give it a yellow touch to all the samples. Now look, the ensemble behaves much better. Ensemble behaves sorry. And let's see what happens after like 20 steps. Okay, now the ensemble predicts the data pretty good. Finally, we have the ensemble like this. With this good-looking classifier, we conclude our tutorial on BuildAndCheckAdaBoost and do some NumPy and Python ABC and exploring, visualizing the data and the behavior of algorithms.